In this video, we'll move into Chapter 7, starting to discuss random variables from Section 7.1 and then probability distributions in Section 7.2. 7.1 is a pretty short section in the book. The first thing we establish is this definition of a random variable. Literally from the book, it is a numerical variable whose value depends on the outcome of a chance experiment. Okay? A random variable is essentially what are we measuring when we ask a question. So if I said something like I'm looking at study time for students and I'm trying to measure that, the actual study time would be a random variable. If I'm looking at a family that has a lot of children and I want to look at how many girl children that they have, then my variable would be the number of girl children. So it sounds a little obvious, but just going back to that idea that we kind of already have that sense of variable is a letter in place of a number. So very often we still see that idea x, but that x here is what we're actually measuring. So if we're talking about the number of hours of sleep or the number of televisions that are in a family's house, or if we're looking at the number of electronic devices someone owns, the amount of time that they spend on Facebook, any of those different types of questions, the X itself would be literally what we are saying, and then the data we receive, well, the numbers we receive would actually be the data. So we often need to establish what that variable is. And then once we have a variable, we've kind of covered this before, but a reminder, we can also have variables that are discrete, and they could also be continuous. And going back, we established this a while back, a discrete variable is one that only takes whole number values, right? That really translates, right? No fractions, no decimals. As I was running through some of those examples a few minutes ago, how many girl children do you have? You don't have 2.5 girls or 2.1 girls. You have 2 or 3. How many TVs are in your house? You don't have 5.6 TVs. You have 1 TV, 2 TV, 3 TVs, etc. But if we want to talk about continuous, well, those are values. I believe the book talks about that interval idea. A variable is continuous if the set of possible values are an entire interval on the number line, but really that just means that the value can have fractions and decimals. So if I asked, how long did you sleep last night? You may say 7 hours, but you can sleep 7.1 hours or 7.6 hours or 8 2/3 hours. Fractions and decimals certainly are possible. How long did you study? You may give me an answer like 30 minutes or 50 minutes, and that feels like it's whole number, but just remember, there could be fractional or decimal minutes. We're probably rounding off when we say 30 minutes. Maybe we spent 28 minutes and 46 seconds, okay? So things of that nature. It's easy to just automatically think things are only whole numbers because that's commonly what we receive, but we have to establish the possibility of fractions and decimals. So that's really it. That's section 7.1, being able to establish a random variable and then being able to classify them as either discrete or continuous. So the bulk of this video is going to get into section 7.2. We will look at probability distributions, but we're going to focus on discrete random variables, probability distributions for discrete random variables. So, what we have here, we will get back to 7.3. We'll talk about the continuous random variables. That may come up in a later video, or I'll just say it at the end of this video, and that'll be something we establish a little more. But if we have a discrete random variable, what we can do here, the whole idea of this probability distribution is that we'll make this very simple chart. The books sometimes like to make these as 2 rows. I typically make them as a column, but either way, establishing this chart, where what we need to do to make this chart is when we're looking at x, we have all possible values for x. They are all 100% completely established. Every possible value goes on the chart. Okay? Remember, that's a big reason, a big difference between discrete and continuous. The possibility of fractions and decimals, we could never get every single value on this chart because there's just too many. Every fraction and decimal, there'd be an infinite number no matter how small the interval actually is. So that's going to be a big difference. But for right now, we have discrete, so we get every single possible value that that variable can assume, every possible data value that we can get. And then the p of x would be the probability of that particular value. So that's really all there is to making the chart itself. And the book established this right off the bat. They have a little bit of notation, and I want to talk about a few properties, and then we'll make a few of these distributions. So, what we want to establish. Well, these are probabilities. So, as we've always said, the probability is always between 0 and 1, right? That's a probability fact. That's not changing. Even as we're getting lots of probabilities, each individual one has to be between 0 and 1. And the second fact, let me just break this properties. That's number 1. The second fact, if we add all the probabilities together, we'll get exactly 1. Right? If we list all the possible x's, well then one of them must happen. So therefore all the probabilities equal 1 to guarantee one of the events. And one more time, as long as we have all possible values listed here, then one of them must happen. And let's jump right into a quick example. Let's make a probability distribution based on the results of rolling a single die. And really, whenever I say a single die, I'm always talking about a 6-sided regular die. A set of dice, but just having one of them is just a die. So, the probability distribution, x and p of x. What are the possible values from rolling a die? That's where we have to start. What are all the possible outcomes? Well, the possible outcomes are we roll a 1, a 2, a 3, a 4, a 5, or a 6. That would be every possible outcome from rolling a die. But now let's take that a little bit further. What's the probability for each one? Well, there's 6 total possible outcomes here, and each one of them appears 1 on the die. So each one of these has a probability of 1/6. Every outcome listed. Now, this is just a coincidence, right? This is just one problem. Plenty of other problems, we will not get the same probability, but we figured out the probability for each one individually. Come back here, think about your properties. Every probability, a fraction or a decimal between 0 and 1. And if you add this column, add all the probabilities together, 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 does indeed equal 1. So that would be a probability distribution chart for rolling a single die. Let's take a look at another one. Let's say you have 3 children. Let's make a probability distribution chart based on the number of, let's do male children, the number of boys out of those 3 children. Well, my XP of X, I'm looking at the number of male children. Well, there's certainly a possibility. I have 0 males, that they're all girls, 3 children, all 3 are girls. Well, I could also have 1 boy, and then the other 2 would be girls. I might have 2 boys, and the other 1 is a girl, or I might just have that all 3 are boys and 0 girls. So it kind of feels like each child there's 2 possibilities, but we're really, and even though I keep establishing both boy and girl, I'm really just focusing on the boys, on the number of males. Probability here is a little bit tougher, okay? I'm going to go backwards, and I could either make a nice display showing all the possible outcomes. I can make one of those tree branch diagrams, but instead of being that complicated, I'm just going to be very methodical looking at all the possibilities. I'm going to remind you very quickly of the counting principle. 3 children, so I'm going to establish 3 slots, but how many total possible outcomes are there? Well, how many possible outcomes are there for each slot? The first child, well, there's 2 possibilities, boy or girl. Second child, 2 possibilities, boy or girl. Third child, 2 possibilities, boy or girl. This would give you 8 total possibilities. So my probabilities are going to be something out of 8. But now let me just be methodical. What are all 8 of these outcomes? Well, let's think about how many ways can I have 0 boys. I have all 3 girls, and that's it. That's the only way that I end up with 0 male children. So that's 1 outcome out of 8. So the probability of having 0 boy children is 1 out of 8. But now, what about having 1 boy? Well, maybe the boy is the first child, and then the next 2 are girls. Maybe the boy is the middle child. Maybe the boy is the youngest child. So there's 3 different situations, but each has only 1 boy. So 3 possibilities that satisfy what I'm looking for, 1 male child, out of the 8 total possibilities. Keep going. Very similarly, how can I have 2 boys? Well, I can go boy, boy, then girl. I can go boy, girl, boy. Or I can go girl, boy, boy. Every single one of these situations gives me 2 boys, 2 male children, again, out of 8 total possible outcomes. So 3 out of 8 is the possibility, the probability that 2 out of the 3 children would be male. And then finally, what's the situation? How can I have 3 male children? Well, they're all boys. By the way, that is the 8 different outcomes from having 3 children. I'm doing this problem based on children and looking at boys and girls. This would be the exact same situation if I talked about flipping a coin. If I flipped a coin 3 times and wanted to keep track on the number of heads that I got, you'd have the exact same situation. 0 heads, 1 head, 2 heads, 3 heads. 0 heads means all 3 flips were tails. 1 head means 2 flips were tails. 2 heads means 1 flip was tails. And 3 heads means 0 were tails. The exact same scenario we have here. 3 times we flip. Each time we flip, there's 2 possibilities, 8 total possible outcomes. And you could have like tails, 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 heads, tails, tails, same exact situation. But to finish this problem the way it was, focusing on number of children, 3 boys happen exactly 1 time out of 8. In these first couple, I'm getting fractions here. We will get some others that the probabilities will sometimes be decimals. You could certainly make these decimals, but these just were a little bit easier to establish with just the fractions that we had. Okay, let's move on just a little bit more. What do we think? Let's establish a new problem here. Let's make another distribution. And now let's get some more information. The first 2, nice examples, some good reminders about probability. But now let's start to get to a couple more little situations to consider. This next problem Let's think about this. We survey students based on the number of hours, let's do the number of hours of sleep last night. We received the following responses. I know I just mentioned in a moment ago, hours of sleep is really continuous, but you'll notice as I present the information, it's really going to come out in a discrete format. So we received the following information. We had 23 students slept 5 hours last night. And then we had 38 students slept 6 hours last night. 43 students slept 7 hours last night. 18 students slept 8 hours last night. And then finally, 15 students slept 9 hours last night. That is every single response we received. And now we get the question, well, it's not really a question, the directions. Let's make a probability distribution chart based on the number of hours of sleep. Okay? This is very important to establish. Based on the number of hours of sleep. It's such a common mistake that when people see a problem like this, they start getting their X and their P of X and they goof it up. They just have a lot of information and they just plug in wherever they can and they don't really think about what they're trying to establish. So a very common mistake, people start using their X's and they fill in the 23, the 38, the 43, and so on. That does not make any sense. The question, the directions say, make a probability distribution chart based on the number of hours of sleep. That is our variable. So these are the possible values for that variable. These are the X's. X's will be 5, 6, 7, 8, and 9. Just before I keep going here, especially when people start doing some of the problems here, there are a lot of these that start with X's 0. But this is just a good example to realize it's based on what answers you received. What are the possible answers? Well, there are some others. It's possible somebody only slept 4 hours or 3, or somebody slept 10 hours or 11. But based off the information we receive, we've covered every single possibility here. So these are our X's. But now, what about the probabilities? Here's mistake number 2. People get the X's right, they establish the number of hours here, but then for the probability, they just write 23, 38, 43, and so on. That doesn't make any sense. That's not a probability. A probability has to be between 0 and 1. So what are we supposed to do here? Realize we need the total. If I know 23 students slept 5 hours, that's giving me the number that satisfies what I want. I need the denominator. Out of how many? And the how many will be the total number of students. So 23 plus 38 plus 43 plus 18. We have 137 total students when I actually look at this list. So now when I start thinking about what's the probability you slept 5 hours, well, 23 students slept that long out of this many, so the probability would be 23 out of 137. And now my fractions are starting to get a little uglier, especially when we do the next section. 7.4 will be the next big section we cover, and we'll start talking about more computation, mean and standard deviation. That becomes more of a section where people would rather deal with the decimal here instead of the fraction. So you can make it a decimal, but it's perfectly fine. I'll leave it just like that. Let's keep going. What's the probability you slept 6 hours last night? Well, 38 people slept 6 hours out of the 137. So 38 out of 137 is that probability. And we just keep going. So 43 out of 137 is the probability you sleep 7 hours. 18 out of 137, probability you sleep 8. 15 out of 137 is the probability you sleep 9. They're all a common denominator, so just adding them the way they stand, you'll get 137 over 137. But even with the decimals, sometimes with rounding, we might get the total probabilities like 0.99 or 1.01. That would just be a tiny bit based off of rounding, but it would still be right in the ballpark, if not exactly 1, if you set your probabilities up correctly.